Welcome to the trial lecture of Benedikte Wallace. My name is Alexander Jensenius and I'm director of Ritmo, where Benedikte has been carrying out her doctoral work. Later today, the doctoral candidate will defend her thesis in public, and the committee consists of Associate Professor Sarah Fedeli-Aloui from the Université Paris-Saclay in France, and Professor Geraint Wiggins from the Vrije Universiteit Brussels and Queen Mary University of London, and Professor Karsten Grivots from the Department of Informatics here at the University of Oslo. But first, we have the trial lecture, and the title is The Advancement of Creative Computation by Machine Learning and Artificial Intelligence. The floor is yours, Benedikte.
Hello, and let's see, and welcome. Thank you all for being here today with me at my trial lecture. I have been given the topic, the advancement of creative computing by machine learning and artificial intelligence. I'll try my best in this lecture to build some intuition, both around some of the machine learning methods that are commonly used in creative computing, and our intuition about what the goals of creative computing might be. So to start us off, let's have a look at what is meant by creative computing. So one of the ways of thinking of this is that creative computing is when people use computers in creative activities. And this is characterized by creating something which values expressivity over function. Now, creative computing is a term which encompasses a very large area of study. We can be creative in all sorts of ways with computer technology, and it's a big part of many creative practices. We can, of course, think of many examples of this, since computers are so pervasive in so many aspects of our daily lives. In music creation, digital art, video games, creative writing and photo editing, all these activities in large part require the use of a computer. It can be a tool to create art, a canvas for displaying artworks, or as sketchbooks for artists to develop their creations. The computer has also made these artistic practices available to more people. A democratization of a creative toolset. Something we can see perhaps most clearly in the amount of creative or of independent music artists that have become known today, and the availability of music production software paired with these massive social networks such as TikTok is part of why that's happened. So we can see this everywhere. In 2019, Spotify claimed that 40,000 tracks were added each day to its platform. And then 2 years later, the number is already 60,000. That's almost one per second. And YouTube uploads have gone from 6 hours of video per minute in 2007 to 500 hours per minute in 2020. And who knows how many TikToks are posted each day. Now, using computers in artistic activities is, of course, not a new idea. One of the first descriptions of the creative potential of computers came from none other than Ada Lovelace, who wrote in her famous notes on the analytical engine from 1842 that she imagined the computer could work not only on numbers and the rules of arithmetic, but on frequencies and the rules of harmony to allow programmers to produce complex symphonies. more than 100 years later, Bell Labs hired Max Matthews, who is by many considered to be the founding father in the world of computer music. He wrote the Music 1, the first computer program capable of producing digital audio with the use of the IBM 704 computer. And then, in 1961, the IBM 794 computer was programmed by Max Matthews to sing the song Daisy Bell. Now, I've decided I won't play this song for you now, just because I find that voice incredibly creepy. If you haven't heard it, please take my word for it, save yourselves, or check it out on your own free time. But creative computing can take many different forms. In the 80s and 90s, creative computing became a movement within alternative practices in computer culture, with participants sharing experimental and artistic uses of the burgeoning computer technologies. The term digital art was actually first coined in the early 80s when Aaron, a robotic drawing machine, which we see here, was used by digital artist Harold Cohen. Aaron is actually claimed to be one of the longest running, continually maintained AI systems in history, as it was, in a way, Cohen's art partner for about 40 years. But it's worth mentioning that creative computing can also have a somewhat broader definition. In 2013, Hugel and Yang laid out three pretty vague, and depending on how you view creativity, it potentially encompasses all computer programs ever written. We can, of course, look at the big transformational computing products like Tim Berners-Lee inventing the World Wide Web, or Steve Jobs and his team developing the first iPhone, or the computing technology behind images from the outer reaches of our solar system. This is Pluto. Naturally, these advances required a lot of creative computing, but a lot of creativity goes into not so groundbreaking computing as well. I would argue that the process of developing code is, by its nature, a creative one. And in this sense, development of any software application or physical device with a microchip involves some kind of creative computing. Take, for instance, the microwave. Now, this is a particularly happy one that has been turned on its side and apparently just absolutely loves it. But there are a lot of creative development decisions that are involved in how we represent its digital interface, how they create and generate the sounds that it makes, and how to make the interface nice to use. So these solutions require a bunch of creativity from engineers, designers, and software developers. So as you can see, defining creative computing as the creative development of a computing product could make this a very long lecture, mostly about microwaves. So to make sure I can finish this lecture somewhat on time, it might be beneficial to narrow the scope a little bit. So let's look at the second type of creative computing mentioned by these authors: the development of a creative computing product. Now, this narrows it down a little further. So we can think of a creative computing product as a product resulting from this process of people using computers in creative activities. One of the first things that might come to mind here are art projects produced using P5 and processing. So in creative computing, the programmer is the artist. Processing and the web-friendly version P5, which is based on JavaScript, allows programmers to create interactable visualizations and also learn to code by creating visual art. The processing framework is a good place to start for those wanting to experiment both with coding and with visual art. And the examples that I have included here show some of the many possibilities. It's also possible to play around with more realistic visuals using something called shaders, which is a method for emulating the light and shade of a 3D environment. And in addition to purely artistic experiments, processing can also be used to visualize algorithms and complex data, such as this, which was made by a colleague of mine to visualize the implementation of L systems, which make these beautiful snowflake designs. And this one, which shows a simulation inspired by Darwin's finches, where each little dot is an evolving finch, and each color represents a different type of food source. Now, the final type of creative computing suggested by Hugel and Yang is the development of computing environments to support creativity. Now, this can refer to supporting a specific activity, such as music making or creative writing. An example of this is the app Writing Challenge, which generates writing prompts for creative writing projects that can often be purposefully weird or funny, and they aim to kickstart your writing project by giving you these daily tasks and daily prompts. There are also applications that aim for creativity support. So far, we've seen 3 definitions of creative computing, some very broad and others more distinct. To summarize, we can say that creative computing is a field of research and development that aims to allow people to engage in the creative process using computers. So what exactly is this process? Well, the creative design process has been studied in various fields. And in a paper from 2008, authors compiled a description of the creative process within engineering fields and cognitive psychology literature. And they discovered that there were a lot of similarities across various disciplines. This process consists of 5 stages: formulation, synthesis, analysis, evaluation, and documentation. Now, this process is probably recognizable to many of us, though we may have seen other words describing each stage. I know I recognize it, both from working on creative projects, research, software development, and probably a myriad of other things too. So the first stage, formulation, also called often the motivation phase, involves conceptualizing the desired behavior of the system. So this is usually where you map out the path to your desired goal, decide on what methods to use and what tools to use. Synthesis refers to the process of implementation. Here you start actual creation and build towards this desired goal. The analysis and evaluation stages involve observing the behavior of the system after implementation and evaluating whether the system acts in the way that you intended. And the final stage is documentation or dissemination. This is the manufacturing stage, where the system or product that you have created is unleashed into the world and can receive feedback from others. An important part of this process, though, is how we often move through it, which is often in a non-linear way. As we reformulate ideas, we change our approach, we evaluate, and then maybe start over. So creative computing both facilitates this process and relies on it for the creation of computer-aided artworks. Now, what we are looking into today is how AI and machine learning has or could advance this process of creative computing and the artifacts that come from it. But before we begin looking at that, I wanted to take briefly some time to address these two terms, artificial intelligence and machine learning, because what is the difference? Defining the term AI could in many ways also be a lecture topic on its own. In preparing this lecture, I have asked colleagues to tell me, what is AI? And many have started their response with something along the lines of, oh, easy. But then continued by following up with a long tirade and leaving us both more confused than when we started. Others, who I can identify maybe more with, responded only with a nervous laugh. And the term AI does have a somewhat fuzzy definition, which is evolving over time and is often used as a broad term which can mean slightly different things in different contexts. In the book Artificial Intelligence, A Modern Approach, we can find a collection of descriptions of AI by many of the pioneers in the field. We can summarize them into 4 groups. Systems that think like humans, or systems that think rationally, systems that act like humans, or systems that act rationally. Now we can further group these definitions into 2 main ideas. We call something AI based on its thought process, that is the processes that govern its behavior, or we call it AI because of the behavior itself. In other words, how we, as humans, perceive it. Take, for example, the program ELIZA. ELIZA was a program developed at MIT in the 1960s, and it's a program we today often refer to as the first chatbot. The ELIZA program included a doctor script, which would take user input and formulate responses in the form of a therapist. The way ELIZA worked was by parsing this input text, looking for keywords, which would then be mapped to certain responses. So while ELIZA does not have the capacity to reason or learn, the program is often, still today, referred to as AI. I actually have an ELIZA script here on my computer, so we can have a look at how it works. Hopefully you guys can see this. Hopefully my nerves will allow me to type. Let's see, I should have just run this. Yeah, so she says, hello, I'm ELIZA. How can I help you today? And I feel like I do need a therapist right now, so say, I am stressed. Why do you think you are stressed? Well, just say today is a big day. Please tell me more. Okay, well, my defense is coming up. Your defense is coming up? Don't worry, you'll do a great job. I mean, you programmed me, right? You must be a genius. So She's very charming. I see why people were so charmed by her in the 60s. But truth be told, I didn't program Eliza. I asked ChatGPT to program her, so I should maybe tell her that. ChatGPT made you. Oh. Well, don't be rude. Please tell me more. Well, do you not like ChatGPT, everyone's favorite thing? Oh, okay, well, I think that's as far as I'm going to get with her. Bye, Eliza. So the code for this script is shown in its entirety here. It's a very short script, only about 35 lines of code in Python. And most of that is the keyword response mappings, including 2 that I added specifically for today. And depending on your definition of AI, how you describe Eliza will change. The program does seem to display some human-like behaviors, but the process which makes this possible does not look much like human or rational thought. Now, machine learning luckily has somewhat of a clearer definition. The field of study that gives computers the ability to learn without explicitly being programmed. Now, this definition is often attributed to Arthur Lee Samuel, who in 1959 applied machine learning to teach a computer to play checkers. We can think of machine learning as a method of extracting information from data in order to make decisions, predictions, or recommendations. Now, often the term AI is used to describe something which is in fact ML, and I am absolutely guilty of this myself. In my publications and talks, I often use the term AI, and I might do so even in this lecture, out of habit, but I'll try my best to be precise. It's not that it's necessarily wrong to call something AI, which is ML, because we can view AI as a superset of computing methods that include more specific approaches like machine learning and deep learning. So let's have a look at how AI and ML approaches can be used in creative computing. As an AI practitioner, I try to remind myself that not every situation is improved by AI. And in creative computing, there are lots of examples of projects that require no AI, no machine learning, just code, such as the processing examples that we saw earlier. However, depending on what you want to create, AI can be a big help. So let's look at machine learning in particular. ML has the ability to model complex relationships in data, relationships that might be really difficult to describe in code. So take, for example, the task of writing a program to determine whether or not something is a cat. You might try to write a comprehensive description of what it is to be a cat. So it's small, it's furry, it's cute, thinks it's better than you, it has pointy ears. But there are so many edge cases that you would soon come across an example which passes your checklist but is not a cat. So instead of coding this relationship between some input and the desired output, machine learning allows us to model these correlations by providing examples. These examples can include almost anything that you can collect into a data set. X-ray photos to help with identifications of diseases, examples of singers to replicate a human voice, or sets of images and art to create image generators such as Midjourney. For some complex interactions, we might need these data sets to be very large. But a lot can be done with relatively few examples. Let's have a look at the program Wekinator, developed by Rebecca Fiebrink. Wekinator can be described as a meta-instrument, an instrument that makes instruments. It is a software that combines machine learning with sound synthesis and interaction mappings. The user can supply Wekinator with examples of what sort of input should relate to specific output. And this input can come from your computer, video, trackpad, or keyboard, or from externally connected USB devices. The machine learning part of the Wekinator includes a group of supervised learning algorithms. These are different algorithms that all have in common that they learn by example. So if we go back to our cat detector algorithm, we can replace our description with a collection of images of cats and images of not cats. We then train the algorithm by having the model try to guess whether an image contains a cat or not. At first, the model's suggestions will be pretty random, but for every image, we supervise the output and give a correction. And when I say that we supervise the output, I should make it clear that this happens automatically, because all our examples will have an associated label describing whether or not it is a cat. In Wekinator, each example that you provide needs one or more of these labels so the algorithms can learn to identify them. And by collecting the examples you provide, the ML part of Wekinator learns to classify new input. And users can correct mistakes or reinforce wanted behaviors simply by adding more examples. Now, since Wekinator does not require the user to program anything themselves, it allows people without a computer science background or knowledge of machine learning to create really cool, unconventional musical instruments, such as this one, which is Michelle Nagai's Martlet. It's a wearable hunk of tree bark, which has been fitted with light sensing sensors that control sound generating software. But you can also map your input to other things than sound, like this facial expression to meme classifier by Andreas Refsgaard. Might be useful. Or this adorable cardboard robot called Highbot, which detects you waving and waves back. One of the biggest hurdles for people to get into machine learning is programming skills and the access to large data sets. And since Wekinator allows you to supply your own examples, you can build small niche data sets specific to your application. And this also lowers the bar for people to play and experiment and, most importantly, make quick prototypes. Another really cool example is the project Dance On. The Dance On technology enables users to upload dance videos or use their webcam and write code that creates responsive animations based on pixel location data and pose detection algorithms. So here, developers created a domain-specific language for combining virtual shapes to movements, which allows the users to also have this instant feedback. One of the design goals specified in the Dance On project was the idea that art motivates code, and that code motivates art. And this reflects back on what we know about this creative process loop and the importance of being able to quickly prototype and test new ideas. The Dance On technology utilizes pre-trained pose recognition models and motion tracking software. So this way, the machine learning models are all under the hood of the Dance On program, making it so that users can utilize these methods without having to implement and train these models themselves. So creating systems like Dance On, which take advantage of pre-trained machine learning models, lets people build advanced projects and get to know the affordances and limitations of these models, and create things that would basically not be possible without pretty advanced machine learning tools. As another example of using pre-trained models in creative computing, we have Magenta Studio by Google. Now, the Magenta team have been working on deep learning models of music for many years. Their models are often state-of-the-art, they're large, they're trained on huge data sets. And though their research has resulted in a lot of very interesting developments, these methods are not something that most of us have access to. So let's have a quick look at two of their most used models, the recurrent neural network and the variational autoencoder. So the recurrent neural network, or RNN, is a sequence prediction model that learns to predict upcoming events based on previous events. So these models lend themselves well to data where chronology, or the order of events, matters, such as music and text. So where a regular artificial neural network might look something like this, where we have a set of interconnected neurons, a recurrent neural network includes internal recurrent connections within each neuron. And this allows each neuron to not only be affected by whatever the current input is, but also the sequence of events that preceded it. It holds a sort of short-term memory. But these recurrent connections mean that we need more computational power. And the longer the sequence is that you want to model, the more likely the RNN is to forget things that happened further back in time. And this can make the RNN difficult to train, especially on the fly. The other model I wanted to briefly mention is the variational autoencoder, or VAE. It's another popular machine learning model in creative applications. It consists of two neural networks, one which learns to squish the input, compress it into a more sparse representation, and one which learns to decompress it back to its original form. By doing so, a VAE creates a sort of continuous landscape of encoded versions of the training data. This encoded landscape is called the latent space. And as an example, let's represent this latent space as this cluster of different colors. If two inputs are very similar, they will be encoded close together in the latent space. And if they are very different, like the circle, square, and triangle, they will be further away from each other in the latent space. Now, what makes the VAE interesting is that the algorithm ensures that this latent space is continuous, which just means that it has no holes, no missing data. It is a complete map. So if we look at two inputs that are far apart, the VAE also creates the encoding for sort of the midpoint between these two, and for 3/4 of the way, and so on continuously. So the Magenta team trained a VAE on a data set of melodies to make their music VAE. By inputting any two melodies, the encoder of the music VAE encodes them into this latent space and allows us to interpolate between two different melodies that are far apart. So that helps us to sort of mix two melodies together, similar to how a painter would mix colors. Now, training something like the RNN or the VAE requires a lot of data and a lot of processing power. Their training data consisted of 3.7 million melodies, and the algorithm was trained for around 100,000 epochs. Now, depending on how quick your computer is, how long that'll take will change, but suffice it to say it will take a long time if done on your laptop. But recently, Magenta have made some of these big models available as MIDI plugins for the music production software Ableton Live. These are adapted using the integrated Max for Live environment, a callback to Max Matthews there, a version of the Max Visual programming language specifically integrated into Ableton Live, and therefore natively available to all users of Ableton, without requiring any knowledge of ML or programming. These plugins are made easy to use and fast to use, and consists of 5 different models that each serve a specific purpose. Continue is a plugin based on an RNN, which you saw earlier, which generates notes that are likely to follow your drum beat or melody. Interpolate allows users to combine and shift between two melodies or two drum beats by traversing this latent space of Magenta's music VAE. Groove and Drumify adjust the timing and velocity of an input drum clip, or generates drum beats from any rhythm of any input. And lastly, they include a program or a plugin, Generate, which can produce a melody without any input primer. So under the hood, Generate uses a variational autoencoder that has again been trained on millions of melodies and rhythms to learn this sort of summarized representation of musical qualities. Generate then chooses a random combination of these summarized qualities and decodes it back to MIDI to produce a unique clip. In addition to providing access to Google's large pre-trained models, all of the plugins have this temperature slider. Now, temperature is a parameter used for sampling from the last layer of a neural network. It allows us to add some unpredictability to the generative process. You can think of it as controlling randomness. So higher temperatures produce more variation and sometimes even chaos, and lower values are more conservative in their predictions. So as an example, think of the task of predicting the next note in a melody based on the sequence of preceding notes. So our prediction models will usually aim to learn a probability distribution between all of the possible next notes. So in this example, the model would try to find the likelihood associated with each of the 12 notes. So you might end up with something like this, where the height of each bar represents the likelihood of each individual note being chosen next. So since the model learns what the most likely next note is, based on the preceding notes and how often each note appears in our training data, we have the option to ask the model to predict the most likely note. But that will probably produce quite conservative and uninteresting things. So using a very low temperature here would result in us picking F as the most likely. However, by choosing D, the second most likely, we might get something that was more interesting. So to amend this, it's common to use this temperature parameter to reweigh these learned distributions in order to make it more likely that other notes are chosen some of the time. So higher temperatures, again, produce more variation and sometimes chaotic results like this, and lower values are more conservative and give us the more likely answer. But this additional potential for creating variations broadens the possibilities of what these plugins can create and adds an additional layer of unpredictability, which can be a lot of fun to play with. And this is one of the ways that we can see AI and ML potentially improving creative computing. When discussing the future of creative computing, Hugel and Yang, who I referenced before, write that the challenge is for software to become a more effective servant of people by being more adaptive, smarter, and better engineered to cope with the frequent changes in direction, inconsistencies, irrelevancies, messiness, and all the other vagaries that characterize the creative process. And it is this messiness that we might fear losing when bringing computers and technology into our creative practice. But I would argue that there is a lot of chaos and messiness in programming, and with the use of AI and ML, we can capitalize on this chaos in some really interesting ways to broaden our ideas. So as a final thing, I couldn't resist. I wanted to show you guys my perhaps favorite examples of a machine learning algorithm misbehaving during the creative computing or the creative problem-solving task of playing hide and seek. So this is OpenAI's reinforcement learning testbed. And these little guys, the blue ones, they will be hiding, and the red guys will be seeking. And they have this little environment, as well as some items like these boxes and the ramp that they can move around and lock into place, either team. In reinforcement learning, as the word implies, the algorithm improves by trying out different things in its environment, and when some set of actions leads to a team win, the team receives a reward. So here in the beginning, it's all mostly chaos and randomness. But as the training continues, you can see the blue team discovers a winning strategy, which involves moving the boxes into the door openings and locking them in place so the seekers can't get in. So victory goes to the blue team. But after some rounds of this, the red team discover that they can use the ramp. They can sneak in, use it to move it across the screen, and jump over the wall and enter the blue's room. So victory to the red team. However, this does not last long, as the blue team has just enough time while the seekers are counting to sneak out, grab the ramp, and run back into the room. I notice that you are all sort of rooting for the blue team. I think that's very unfair. Because this last moment is what I actually wanted to show you. So here we're on a different map, and this red guy does something which is not a valid action. Something the developers had not accounted for, which is outside the rules of their environment. So by running up the ramp, the red guy lands on the box in such a way that it becomes a skateboard that he can ride around and get into the blue's hiding place. So basically, red has learned a speedrun strategy. Now, my point here is that the surprise of this unpredictable action gives me joy and exemplifies exactly how ML algorithms can occasionally bend rules in a really fun, unpredictable, and even creative way. So to summarize, using AI and specifically ML in creative computing is useful when working with complex data like movement, sound, and complicated interactions. It also allows us to model situations where programming would be very cumbersome. This can help in lowering the bar for participation by allowing people with less programming experience to be part and to experiment. And by playing around with sort of the misuse of ML models, we can also create unpredictable and novel experiences. So in the future, if we dare to dream that computational power and resources continue to grow and become available to more people, it's easy to imagine ML-powered software allowing us to explore interesting combinations of different fields and methods, exploring complex relationships between different source materials, and allowing more people to create big or small expressions of their creativity. That's it for me. Thank you.
Thank you very much, Benedikte. There is now a break, a lunch break, and we'll reassemble here back at 1:15 for the public defense.
Distinguished members of the committee, dear colleagues, ladies and gentlemen. My name is Andreas Austeng, and I'm a professor at the Department of Informatics, University of Oslo. Yes, please sit down. Okay. As the appointed moderator, or the custos, it's a pleasure to welcome you all to this disputation on the dissertation submitted for the degree of PhD at the Faculty of Mathematics and Natural Sciences at the University of Oslo. The faculty's PhD program council granted Benedikte Wallace application for admission to the PhD program on the 30th of August 2018. On the 30th of May 2023, Benedikte submitted her dissertation entitled AI-Generated Dance and the Subjectivity Challenge. The supervisors for this work has been Dr. Charles P. Martin, College of Engineering, Computing and Cybernetics, the Austrian National University, Christian Nymoen, Department of Informatics, University of Oslo, and Jim Torresen, Department of Informatics, University of Oslo. On the recommendation of the Department of Informatics, the faculty appointed the following adjudicating committee. Associate Professor Sarah Ftili Alaoui, LISN, University Paris, Saclay, France. Professor Gerard A. Wiggins, Computational Creativity, Vrije University, Brussels, and Queen's Mary's University of London, that's Belgium and UK. And Professor Karsten Grivots, Department of Informatics, University of Oslo, Norway. The adjudicating committee reported on the 7th of August 2023 that it had found the dissertation worthy of being defended for the degree of Philosophia Doctor. The candidate presented the required trial lecture on the prescribed subject entitled The Advancements of Creative computation by machine learning and artificial intelligence. The adjudicating committee has found the trial lecture satisfactory. During the disputation, Associate Professor Sara Fdili-Aulai and A. Wiggins will act as opponents. First, the candidate will give us a brief survey of the purpose of the work and the results of the investigation. Then, Associate Professor Sara Fdili-Aulai will put the work into an international context and present her opinion on the dissertation. Afterwards, Professor Gerard A. Wiggins will continue the opposition. The candidate will be allowed to answer the comments or questions from the opponents. Finally, it will be possible to speak ex auditorio. I now call on Benedikte Wallace to present her scientific work.
Thank you. I would like to begin my presentation by thanking first off my defense committee for their work in reviewing my thesis and articles and for being present here with me today. I would also like to thank my supervisors Charles Martin, Christian Nymoen and Jim Tørresen for guiding me through my work and helping me get to this day. So let's start off by explaining the title of my thesis, AI-Generated Dance and the Subjectivity Challenge. At the outset of this work, the preliminary title for the thesis was AI-Generated Dance, Deep Learning with Multi-Dimensional Time Series Data. And yes, deep learning is the underlying method used in most of my work. I was motivated to use deep learning due to this method's ability to model complex correlations without explicit programming. I was curious to explore whether deep learning could model the complex interactions between dance movement and music, and what we might learn about how music moves us in the process. But the title of my thesis did ultimately change. And there were two main factors that led to the addition of this concept of the subjectivity challenge. Firstly, seeing how my own work and not least the work of others were solving some of the first sort of technical challenges around generating realistic dance movement, these works began answering some of the previously unsolved questions regarding how. And secondly, I was able to engage more with dancers and movement practitioners, dance anthropologists and researchers. And this motivated questions more related to why generative AI in dance. These factors brought a different set of questions to the forefront. What makes an artistic artifact good? And what should be the aim of a generative model of art? In this thesis, I've used the term the subjectivity challenge to refer to challenges related to teaching a machine to generate artistic output that has some value. And in this thesis work, I've attempted to clarify ways in which we can approach these challenges. We can further frame my work through three research questions. The first is mappings. What can AI-generated dance reveal about sound motion mappings? While dance can, of course, exist without the close relationship to music, it's clear that music has some effect on how we move, both in dance and in other movements, such as walking, or even when explicitly trying to stand still. When we look at these two stick figures, I'm sure many of you have some idea about what music might have been playing when each of these recordings were made. So our hypothesis here is that moving in a reasonable way to different musical stimuli would be a crucial step in creating realistic AI models of dance movement. The second research question is about control. How can we influence the outcomes of the models? This research question is motivated by the idea that variation is an important aspect in modeling any creative activity. Since deep learning methods usually result in large models that take a long time to train, it can be beneficial to establish what variations are possible after training. Further, understanding the effects of altering parameters of a model after training allows us to probe the limits of its generative power. The final research question is given the header practice. What role could an AI dancer play in the creative practice of dance? We have seen examples of how creative fields have been impacted by generative AI, particularly digital artists after the influx of image-generated models such as Midjourney and DALL-E. Dance generation systems have yet to become particularly widespread, and so we have an opportunity here to monitor the experiences of dance communities and change our methods to promote closer collaboration with these groups, mapping out how AI could play a role in their practice. So these research questions were approached in a somewhat linear fashion across 6 papers, beginning with mappings and ending with practice. So today I'm going to present a summary of these publications and then tie them into my research questions as well as the subjectivity challenge. The first paper, Tracing from Sound to Movement with Mixture Density Recurrent Neural Networks, explored the ability of deep learning models to learn sound motion mappings using a dataset of sound tracings. The sound tracings are simple movements performed by moving a wand through the air. The dataset collected by Christian Nymoen in 2010 allows us to begin implementing a deep learning model for generating movement based on sound and movement features, while still being simple enough, i.e. a single point of movement as opposed to full body dance movement. The model that we used in this work is a variant of a recurrent neural network with LSTM cells in combination with a mixture density network. Mixture density networks, or MDNs, treat the output of our neural network as the parameters of a Gaussian mixture model, which can be sampled to generate real valued predictions. This approach also has the advantage of gaining control over the number of mixture components, and this allows training to account for situations where multiple predictions could be considered equally suitable. The result of using an MDRNN to generate sound tracings revealed that the MDRNN managed to learn an approximation of the movements in quite an interesting way, picking up on some of the tendencies shared between the examples of different sounds in our training data. So we decided to explore this model further when moving towards more advanced full body motion capture and dance. So in order to examine more complex sound motion mappings and attempt to train the MDRNN to generate full body dance motion, I began collection of my own data set of improvised dance here at the Ritmo Motion Capture Lab. The dataset consists of full body motion capture recordings of 30 participants and 6 one-minute musical excerpts that were used during the performances. So participants performed 3 improvisations to each of the 6 musical stimuli, and this results in 18 recordings per participant and 540 one-minute recordings, which is about 9 hours of data in total. The motion capture and audio data has also been made available online as an open access dataset. So using a subset of this new dataset, we applied the MDRNN model to it to see if we could generate realistic-looking dance movement and how the musical features from the audio in our data might be used to affect it. The generative RNN used in our previous work was rather small, consisting of 2 layers of LSTM cells, each with 15 hidden units. And to deal with the added complexity of the full body motion capture data, we extended this model to consist of 3 LSTM layers containing 1024, 512, and 256 hidden units, respectively. The outputs of this third LSTM layer are in turn connected to a mixture density network. The LSTM layers learn to estimate the mean, standard deviation, and weight of the 4 Gaussian distributions of the MDN. To examine to what extent this model then has learned a correlation between the audio features and the movement, we experiment with generating motion using audio features from different audio sources. And we found that the MDRNN's output had learned some mappings between sound and motion, with unfamiliar features causing noise and jitter in the generated dance, as can be seen particular in these last 2 examples. In our third publication, we wanted to further explore the limits of this model's generative capabilities. When using generative deep neural networks for creative applications, it's very common to explore multiple sampling approaches to generate variations after the model has been trained. And this sampling stage is a crucial step, since choosing suitable sampling parameters can make or break the realism or perceived creative merit of the output. So in this paper, we explored 3 common strategies: primed sampling, temperature adjustment, and isolating mixture components. I wanted to highlight the results of the last strategy here in particular, as the other sampling strategies are common for most models that learn to predict a probability distribution. Isolating mixture components is unique to the mixture density model. We found that each component had learned a different possible future from a given start pose. And by isolating each component, we can examine what these different futures are. So we chose 4 mixture components for this model, and so we generate a sequence of movement from each component, keeping all other parameters the same. So we have from the most likely predicted component to the least likely. Now, the component with the highest learned likelihood naturally learned the most realistic-looking dance sequence. When sampling from the second most likely component, we get movement sequences that are a bit more distorted, but they're still coherent and smooth. Sampling from the final 2 components resulted in very little movement at all, and the movements that are generated look a bit painful. I've lovingly nicknamed this one the ankle breaker, and I'm sure you can see why. And the least likely component generates quite impractical, if not impossible, feats of balance. However, there are interesting variations to be found in the mixture density network's different components. So in paper 4, we returned to the notion of sound motion mappings. We collected some of the most realistic-looking examples generated by the models trained for our previous publications, and we created an online study of the perceived sound motion mappings of our generated movements versus human movement. So we began by selecting 2 songs from our dataset that were the most different from each other. One is slow with no rhythmical instruments and no clear beat. The other is a pretty straightforward EDM track with a clear beat and a high tempo. To generate stimuli for our survey, we then used the audio features from these 2 songs to prompt the MDRNN. We present then these examples once with their intended song and once with a different song in order to cause a mismatch between the sound and the movement. We also included a symmetrical set of examples from our dataset for comparison, that is, musically matched and mismatched examples of human dancers using the same musical stimuli. And participants were asked 4 questions. The first is how well they feel the movements suit the music. The second is how expressive do they think that the movements are. And the third is how dance-like they think the movements are compared to other types of movements such as skiing or working out. And the third question is simply, do they like it? It's worth noting here that we did not expect the AI-generated movements to score as high as the human movements. The dancers in the dataset are talented, their movements are very expressive, and even state-of-the-art movement models are not at the point yet where they can produce equally expressive examples. However, if the model is doing a good job, we might expect to see the same tendencies across respondents to human and AI examples. Now, in our results, we discovered some things that were as we expected. Firstly, the AI-generated movements scored lower than their human counterparts across the board, so no surprises there. And the perceived musical fit of a given human example correlated directly to these sound mappings. This confirmed that respondents had the ability to pick up on the correlation between the sound and movement in human dance. And we observed some correlation between sound and movement in the AI dance as well, but the correlations were a lot less significant. The highest rated AI example was found to be the animation of our high-tempo song set to its intended music. This was somewhat expected, as early results indicated that our model generally performed better when generating movement for music with a clear beat. The survey results also indicated some not so expected findings. The dance likeness ratings did not correlate to the sound mappings, neither for human or AI examples, indicating that what we might perceive as dance does not always match up with what we feel suits the music. So in the work that we've seen so far, the focus has been a little more on the technical side, looking at how to best train the models and exploring the movement variations that it can generate. In this work, the focus has shifted to how a generative model might actually be useful to dancers in their practice. We were motivated by the questions, does generative AI have a place in dance practice? And what might that look like? Now, state-of-the-art movement models are still developing when it comes to generating output that can achieve the realism and expressivity of human dance. And there exist few, if any, available real-time generation models to work with. So to examine the potential future of generative models in dance, we chose to utilize role play and a speculative design approach wherein the dancers themselves take on the role of the AI. We hosted 2 workshop events, one in Oslo and one in London, wherein dancers were invited to take part in a day of body storming and discussions. And in these body storming sessions, the participants took on the role of the AI, receiving input in the form of movement from the other participants and responding in the way that they might expect or hope that a generative AI would respond. Our discussions at these workshops culminated in a collection of themes: intuiting flow, building and breaking shared images, and going beyond replica. The first theme emerges from the many moments of intuition, kinesthetic awareness, and the lightning-fast prediction that the dancers displayed during their improvisations. The lack of conscious decision-making is crucial to upholding the flow of the improvisation due to the speed at which the interpretations are happening. The complexities that are involved in formalizing these interactions are clearly a challenge for building an AI dancer that can foster this kind of kinesthetic creativity and contribute to dance creation. The theme Beyond Replica aims to encapsulate the concepts relating to the body and the limitations and affordances that participants envision when interacting with a non-human form. While the potential for AI to be non-human in its movements and shape is seen partly as a challenge, it's also seen as a positive aspect. When imagining a collaboration with an AI counterpart, the participants express a desire for an AI dancer which exploits its non-humanness in favor of an AI which is a mere replica. And at the cross-section of our previous themes lies building and breaking shared images. Novelty or surprise is a central aspect of our understanding of creativity, both in humans and in computer systems. And a necessary counterpart to novelty and surprise is the notion of predictability. Participants built a rapport with each other, which they describe as a shared image, an understanding of what they are creating together. And this shared image helps the participants predict what their partner might do next and where the improvisation is moving. But some of the most inspiring moments of improvisation seem to come from those times where this expectation is broken. In my final publication, this notion of breaking expectations and leveraging the non-human features of AI-generated dance is explored together with dancer, teacher, and choreographer Benedikte Wallace. We implemented a simple online browsing interface and facilitated a series of sessions with Bendik where he could use this interface to explore AI-generated dance and glitch as part of his creative practice. These sessions included choreographic ideation, which resulted in the performance that you see in part here. But he also integrated the interface into an improvisation workshop with his dance students. Our findings here revealed a process for which glitch is the catalyst. From surprise as a challenge and a benefit, through the transformation of impossible movements to breaking habitual movement patterns. The moment of disruption caused by an unexpected glitch would often initiate a deeper engagement in translation from the movements performed by the AI to the dancer's own movement language, as they would need to transform these impossible movements of the glitch into their own bodies. Our findings in this study further supported the notion that glitch could function as a practical use case for AI-generated dance, as they motivated the dancers to move in new and unfamiliar ways. This also supports previous research in creative domains, which upholds the importance of surprise and unfamiliarity in creative catalysts. And it supplies a specific example of how this manifests in AI-generated dance. So to summarize, let's look at the conclusions we can draw for the three research questions. First, mappings. Our question here was, what can AI-generated dance reveal about sound motion mappings? Well, from the work presented here, we can observe that while our models were capable of learning an approximation and sometimes a generalization of sound motion mappings in dance, the idiosyncratic nature of movement and music's effect on it makes this a very complex phenomenon to model. And by contributing a unique data set of improvised dance, it's my hope that this can be further explored in the future, not only by ML practitioners, but by scholars from different disciplines as well. The second research question was, how can we influence the outcomes of the models? Through papers 2 and 3, we have created a systematic overview of common methods for controlling the output of our trained models. These findings are also made available as an online code repository. And through our later papers, we've also presented the views of dance practitioners on what methods and levels of control would be advantageous to their practice. This includes shifting between building and breaking shared imagery and expectations, and the potential to determine how the model should interpret movement, either semantically or syntactically. For the final research question, practice, we asked, what role could an AI dancer play in the creative practice of dance? Our findings here corroborate previous research on the importance of surprise and making strange when designing a creative catalyst. We present the use of AI glitch as a potential use case in improvised dance with tests in a real-world scenario of improvisation training. We further identify new perspectives on how an AI dancer might fit into a dancer's practice, which centers the concepts of shared imagery, novelty, and embodiment. So lastly, let's return to the notion of the subjectivity challenge and attempt to apply these findings to the broader challenges outlined at the beginning of this presentation. What makes an artistic output good? Since defining a metric for what gives an artwork quality is such a subjective notion, we have tried to approach evaluation through multiple views, both those of the audience, the choreographer, the dancer, through quantitative measures and qualitative approaches. And within each view, the notion of perceived quality changes somewhat. This shows the importance of a holistic approach to evaluation of creative artifacts and generative models. And when it comes to what should be the aim of a generative model of art, we find that while an often appreciated strength of machine learning, and rightly so, is being able to accurately predict or replicate a desired result based on some input, when it comes to creative application, there is great potential in the messiness and chaos. Our participants take inspiration from being surprised with the unexpected, and being able to manipulate the amount of chaos and messiness can be a powerful tool in the creative process across many artistic disciplines. Being able to faithfully generate ideas based on the user's parameters is definitely useful, but there is also benefit in challenging expectations to potentially create more of a dialogue between artist and computer. So once generative tools get into the hands of artists, that's when we truly begin to see how these new tools can affect the world of art and performance. And in the context of AI-generated dance, this may take the form of using the unreal aspects of an AI dancer to exaggerate or interpret or extrapolate a dancer's movements, forming interesting duets between AI and human dancers, or allowing dancers to explore their own and others' movement languages. However, the impact of AI-generated dance in the future may also take forms that completely escape me at present. As artists continue to incorporate, challenge, manipulate the development and use of generative AI. And so I, for one, look forward to being surprised. Thank you.
I thank Benedikte Wallace for her contribution, and I now call on Associate Professor Sara Fdili Alawi to put the work into an international context, to give her validation of the dissertation and start the ordinary opposition. Please.
Okay. Thank you, Benedikt, for this presentation. Thank you for inviting me here to be one of the opponents for this thesis. Hello, everyone. My name is Sara Fdili Alawi. I'm an associate professor at University Paris-Saclay in human-computer interaction and also in dance, as I'm a choreographer and a dance artist as well. And I was lucky to witness Benedikt's work, to read about it, and also to read the thesis ahead of this defense. So I was asked to put this work into an international context. And for that, I wrote a little text, kind of an assessment with open questions for you to engage in a discussion as well, and also to kind of draw a little bit on the history of this field. But of course, I'll be talking from my own perspective, coming from human-computer interaction in particular, and from dance research. So bear with me as I read this text. I'll try to make it compelling, but also open for conversation and discussion. So this thesis aims to explore the creation of AI-generated dance for improvisation purposes. And as you could see, the concept of the subjectivity challenge is introduced early on in the thesis as the ability to teach machines to generate artistic output that is of value and interest to artists rather than objectively good. Am I right? Because as we know, an objectively good assessment does not exist in arts per se. So Benedikt defined that and defined certain criteria that AI-generated dance needed to fulfill to produce such artistically valuable outcome. The artifact needed to be recognizable as dance, they needed to be useful and interesting, and they need to produce novel output while conforming with the norms of the training dataset, meaning to balance between novelty and typicality. She then goes on to ask what would be the purpose of the AI-generated art, to which she responds with 3 points that I would recall here. Augmented creativity, democratizing art, and revealing something about human cognition, which we saw in your defense. So throughout my reading, the thesis has addressed well these aims and goals through various endeavors, as you could follow. And Benedikt explored the generative possibilities of deep learning models through learning of the mapping between movement and sound. She delved into questions of control of those models to make them more interactive, the exploration of their parameters, and then she delved into the exploration of AI with dancers, with real people, and the potential effects that these models can have on their practice of improvisation. So after this introduction, I'd like to, as I was asked, put the work into an international context. The background of this thesis is grounded in a large and long history of dance and technology. And these interdisciplinary approaches linking dance to technology has actually existed for almost as long as computers existed. And some of the earliest experiments illustrating such approaches are the 9 Evenings interactive performances. You actually cited Bell Labs this morning, so I can talk about some of the performances between sound artists and engineers from Bell Labs in the 60s. And since then, at least my field, human-computer interaction, and researchers particularly interested in creativity and cognition have welcomed a series of work using computation in dance. And this thesis falls under such works. And in particular, we can cite creativity support tools. as here AI is seen as a creativity support tool. So what are these CSTs, what we call CSTs? They usually intervene either on stage, in composition, for learning, or in documentation. And they're designed to support practitioners, here choreographers and dancers, in creating and transmitting their ideas. And I can cite the Schneiderman paper in 2000, very famous paper, a little old school, but still relevant. They focus on allowing kinesthetic creativity to unfold and supporting the generation of creative ideas in the choreographic process through interactive and generative technologies, and sometimes both. And in this quest, choreographic and dance practices are often presented as challenging design space because, as you said very well, they're made of personal and idiosyncratic methods, as well as non-linear and messy processes. And here I can cite a lot of work that I've personally wrote, as I really emphasize how messy choreographic processes are. So within this literature, many systems have been created that are generative. And we can talk about generative system even before we started talking about generative AI, right? So I can think of Scuttle, which you cite, used by Kristen Carlson and designed by her. Another system called Dancing that generates sets of rules resulting in sequences of dance steps. Web3 Composer, Viewpoint AI, developed by Jacobs and Majerko, etc., etc. And in the past years, there have been more experiments with deep learning, and your thesis is one of those. These systems leverage on generative AI to produce creative results autonomously, with systems behaving as creative agents in a collaborative process with practitioners. And to illustrate this, I can cite the collaboration between Studio McGregor and Google Arts and Culture Lab called Living Archive that was released in 2019. It is a tool for choreography powered by deep learning. It is trained on the repertoire of the famous choreographer Wayne McGregor, and it generates movement sequences based on the ones that were trained. And in the words of Wayne McGregor, it creates a live dialogue between dancers and the body of work. So just to make it a tiny bit more provocative, let me delve into the epistemologies and politics and cultures of this intersection between dance and technology. Sorry about this. Not designed for people with glasses. Yeah. So just like the rest of the art field, dance inspires discourse that hand out a special power for technologies, empowering, augmenting, and performers and dancers, and even sometimes autonomously doing their jobs. So such discourse on technological enhancement is sometimes due to the over-enthusiasm that's burgeoning in specialized media and Silicon Valley type culture, etc., but also in our universities. So applied to art, technology is expected to allow for the emergence of what seems like a new form of aesthetics and even a new arts discipline. Now there are many people that call themselves AI artists, as we know. But we also know that technology does not act neutrally as an enabler only. It rather operates on a series of value systems, biases, economics, and political agendas. And I cite the book by Broussard in 2019. But I also want to emphasize that you stated clearly those kind of biases in your manuscript, although you didn't cite them in the presentation here today. We also know that as much as technology empowers, it also disempowers, and examples of using technology in surveillance or political manipulation do not dry up. Another aspect of the politics behind the intersection of technology and dance that I would like to cite is that many of these successful experiments are specific to superstars such as Wayne McGregor, Emil Greco, William Forsythe, and so on, who can afford to gather massive groups of academics and developers to investigate their choreographic approach and visions. The other types of experiments are those that are driven by computer science labs whose researchers care about their technologies, and the goal is always to first develop the technology and then to present a proof of concept for the dancers. And when dancers try their systems and succeeds in the tasks targeted by the tool is considered to be evaluated and assessed. But we also know that this type of artificial context, with artificial tasks, validate the system as supporting practitioners, but there's just too many biases there, and we don't know how these systems would actually serve people in the field. And that's probably one of the reasons why the dance field still lacks a lot of these technological support tools. So I do believe that one of these challenges in designing technologies for artistic practices, and for dance in particular, is to understand how to design artifacts that can apply in the wild and in the studio. And maybe that requires simplifying the technology or doing more research to acquire more in-depth knowledge of the choreographic work, or both. And it's certainly one of the points that I would be interested in discussing with you here or after this defense. So after this introduction in contextualization, I would like to cite what the thesis achieves very well. It narrates the design and implementation of the generative AI model and evaluates it through a survey, and then through organizing a workshop with dancers, speculates on the potential that these AI can have on their practice. All of this is done by summarizing the publication that were produced during the thesis. Benedikte dives into the method used to process the movement generation, mapping motion to sound, the tweaking of the parameters to provide possible controls of the model, the perception of the outcome, and the application of the concept in practice with dancers. And I would like to emphasize once again the care that was given by you, Benedikte, to examine issues related to ethics, privacy biases, and what you call unintended consequences. And this, I think, is fundamental when one works with AI, and I also congratulate you on bringing your voice into that. As I believe the voice of the first author needs to always be situated and their ethical position clearly stated. That's it for my introduction and contextualization, some provocative thoughts. I'd like now to ask a few questions. So the first question for you, Benedikte, is that in the introduction, you start by grounding the work in how AI and deep learning have great potential in many contexts. So my first question, very short question, is it because deep learning have potential that we necessarily need to explore it?
Mm-hmm. Yeah, that's a good question. I think that, at least for me personally, it is this this promise of sort of kind of a landscape that we don't fully understand, and that makes me curious about it, and especially this notion of applying these methods to things where I guess you could say that they don't belong, right? These things that are extremely easy for humans and extremely difficult for computers. Those things in particular, I think that sort of dichotomy is interesting to probe and to see, both because of this potential for actually sort of for us trying to disentangle these like really complex ideas such as creativity and also for what kind of impact that can have on our sort of everyday lives and understanding.
Okay, maybe we can go back to that question later, and I think we will go back to that point of the place of AI in creative practices. Another kind of quick question before we delve into a more complicated one. You state at some point in the thesis that interdisciplinarity leads to awkward approximations. So first, what kind of approximations? And then, how would you advise to add rigor to interdisciplinary work? I would love to learn how to do that.
Yeah, me too.
Genuine question.
Yeah, that interdisciplinarity leads to, remind me what I said?
Awkward approximations.
Yeah. Yeah, I think that, I guess to clarify sort of what I meant by that is that it's referring to, I guess, my own internal challenges of working within several different fields where the views, as you already mentioned, can be so sort of opposite from each other. You can have, like, going from being surrounded by individuals who are as curious as I am about AI to asking people to sort of implement this into their lives and practices where it has not really existed before for them personally, and then seeing that sort of the challenges that brings, and it's also, I guess, specifically referring to approximations that we need to do for taking these huge kind of fuzzy concepts like enjoyment or you know, these vaguer humanities concepts that me as a computer science student didn't really have to deal with before this interdisciplinary work, and trying to translate that into something that a computer or an algorithm can actually, you know, deal with, and that leads to some awkward approximations of these sort of this kind of a Plato's cave situation where the computer has to have more of a simplified, pared down version of these super complex and multifaceted ideas and concepts.
Yeah, I know exactly what you mean with that. Or concepts that are embodied in such a way that they're very difficult to articulate in ways that can be computed.
Yeah.
Right. Great. Okay. I'll keep going with my reading. In the related works, you cite works in dance and tech, movement and computing, creativity and cognition. You dedicate a large amount of space to generative AI and deep learning models, and also to the evaluation of generative AI as it is right now in the related works. You cite. I would be interested in you distilling clearly how your contributions, as you have laid them out today in your presentation, kind of deepen the knowledge of each one or one of these fields, subfields, or combination. And you can go back to the slide where you have your contribution, if that is helpful, or if you have them in mind, whichever is easier for you.
No, I think it's okay without the slide. Yeah, I think again it has been challenging for me, and thank you for situating my work in this, because I find that really difficult to place it within all these sort of different fields. I think that the collection of work that I have produced here and with the thesis has a contribution to take sort of AI first of all. It's I think the main contribution that I see with the work is what we can how we change the metrics or the views what is considered a good output, a model that is performing well. A big challenge for me in doing this is that I use a supervised learning approach, which has an inbuilt constraint where I am basically defining that there is such a thing as a correct next dance pose, which I also fully acknowledge that does not exist. And so I'm trying to counteract that with things like control and adjusting what I can of trying to create something that sort of compensates with this or for this. But the model itself is still underlying it. It is built on the assumption that there is a correct way to dance. So that is sort of a big flaw, and so I hope that through this work it can help as an argument within AI for creating both methods and just discussion around how to deal with that in creative applications, creativity support. When it comes to HCI, human-computer interaction, I guess the takeaway that I hope we can take from this work is the importance of centering the user, the end user, early on in the process. It's something that I didn't necessarily do, and it's something that I would change if I could, in a way, although I am happy with the sort of story and the progress of my work. It does sort of go forward with an example of how much of an effect on your methods, on your evaluations, on your approach it has to actually take part in these discussions with the people who will potentially be using your software. Yeah.
Yeah, this is a great kind of jump to my next question. But I just wanted to say that actually from an HCI perspective, usually we have these three types of contribution. I think you tick them almost all. There's this technical contributions that are possible if you're inventing a new algorithm, a new system, etc. And I think there aren't that many systems out there that are really producing generative sequences of dance that are realistic but expressive at the same time, etc. So your thesis contributes to that as an artifact on its own right. There's aspects of understanding humans as well, which is a second type of contribution, because you've evaluated how people perceive these mappings, you've evaluated how the potential of AI for real people's practices and so on. So these are more in terms of the understanding human type of contributions. And I think one contribution that you have here that you could even explore further is this idea of the subjectivity challenge as a way of evaluating the outcome of an AI generated. So if you could formalize it more and let us understand how we could subjectively look at an outcome and consider it valuable, and who is looking at it, from what perspective, etc., that could be an additional contribution there. And of course, there are also contributions in terms of methods, but these are very hard to do and usually takes more than a PhD. But yeah, this is just some of the what I've seen by reading the thesis. But thank you for making the link to my next question about methods, because yes, as an HCI person, I have these automatism of thinking, we study people first, and then we make the algorithm, or we make the system based on how we study people. And then reading your thesis, I was like, the system comes first here, and then she's speculating about what it could have been doing. Whereas you could have speculated, and then you could have based the system on that. But I understand, I mean, every PhD is its own journey, and every journey is a valuable journey, an interesting journey. And I think also that with a lot of the AI, because these models are so opaque, it's very difficult to actually center them on real users. Because what are you going to change? There are just few parameters that you can tweak, and then the algorithm is anyways its own thing. Or you can train it on different data, etc.
Yeah.
But that's still not that much you can do to design them completely based on your understanding of people. But I would love for you if you can reflect on what do you think, based on what you learned, based on the speculative workshop that you did last, what did that teach you that made you completely rethink what you've done first?
I think the discussions from those workshops really centered for me was and it does seem obviously sort of second guessing myself, or it seems sort of silly to not be like, of course I should have thought of this, from the very beginning. But it was the extreme complexity and the extreme, like we discussed, this like awkward approximation I would have to do in order to try and replicate what these dancers did so effortlessly in their improvisations. That these processes, maybe particularly the way that they, and we sort of group this under this idea of shared images, but the way that they would non-verbally cue each other up with sort of internal jokes or references to cultures or people that they might have met, or just this communication that all happens in the body, and then how they interpret them, which can be done in so many ways, like the way that they interpret a certain movement culturally, just as I said, sort of syntactically, just the movement itself can sort of be mirrored or made opposite, or they can go deep and have these associations to something completely different, and so thinking of like, okay, so how can we try and break this down and approximate it, or make this something that an AI would be capable of doing. And it's a very, for me, it's a very interesting thought experiment to think of like, okay, so a language models and like dealing with the semantics of it on top of an mDRNN, so you can have the variation, and then ultimately it just really put into context this notion that we would have to, that a lot of work remains to make a tool that could be truly useful the way another human is in an interaction like that.
Yeah, no, absolutely. And that makes me hopeful, because a lot of the AI discourse is almost as if you just train a bunch of AI and then it does the job, but then it actually doesn't as much as we're told. It does produce very interesting outcome, and dancers would reappropriate it, would create out of it very interesting sequences. But if you were to actually try and purposefully add into it all of these behavioral relationships that you could observe, then it would be another bunch of years to go.
Many years.
But it's great, because that's what a PhD does, right? It opens a door for a bunch of years of research to come. Great. Maybe I could conclude with how am I doing in time? We good? Yeah, I can conclude with the last question, perhaps. I would like to invite you, just because I was really intrigued by the subjectivity challenge. I have never read about this before, actually. Did you make it up?
Yes.
Yes? Okay. Okay. But I think it's really interesting, and I would be rather interested in seeing how that could be not formalized in a way that's computationally formalized, but just defined in a way that could be useful for others.
Yeah.
That could be maybe reappropriated as a method or as a way to evaluate, etc. And I was wondering if you could do it more as a first-person method, if there was a way for you to formalize what were the subjective kind of decisions that you made throughout the PhD, and how were those made? Like when you look at an outcome and you say this isn't suitable, what makes you say this is suitable or not suitable, or valuable or not valuable, or useful or not useful, and what would you say it makes your collaborators do so? So how can we learn from this idea of a subjectively valuable outcome from an artwork? Do you see what I mean? Meaning I'm not asking to formalize it as do X and Y, but are you looking at something in specific? Are you the one who's looking? How are these design choices made?
Well, the concept sort of sprang from that process of initially doing my very best to avoid adding my own subjective sort of measures of quality and assumptions into the model. It was one of the motivations why I wanted to use deep learning, as you said, which is so opaque, or it is trying with my data set to not sort of represent that data in a way that might have been a lot easier for the model to learn things from, but keeping everything sort of as open as possible and not directing the data or the model in a specific way. But of course that is inevitable, that you leave your mark on this, and so I guess that's sort of where this concept of thinking of that problem as the subjectivity challenge and finding a way of dealing with that, which for me became making sure that although I can't sort of avoid my own subjective ideas permeating the work to some extent, I could at least sort of make sure to make space for other people's subjective evaluation as well, and sort of document how their views on things would impact my work. Yeah.
So did you concretely document how dancers would respond to specific outcomes, or?
Well, in the workshops and in my work more closely in the case study with Benedikte, then yes, we would document this as part of it, but also just in I think one of the first things that happened quite early on in my PhD work was I was asked to present for the Coromundus master's program. So I knew that I would be presenting my work to dancers, dance anthropologists, and I was terrified. I was so terrified. I felt like they would immediately just be like, why are you bringing this nonsense into, we don't need fixing or whatever, and that they would greet me with a lot of hostility. And my reaction was luckily, and it's probably in a very formative moment, was that I was met with the exact opposite. There was so much curiosity about how things worked. I got so many suggestions for have you thought about mirror neurons, and just wild and amazing suggestions. And the one thing I didn't get was fear. It was truly just curiosity. And this also sort of was then something that prompted me to, it was also in these settings that I noticed that the examples that I usually showed more to get a laugh, where I would show how the model was not doing so well, and things I would post online, right, of, oh, look, the model is doing something weird. I could see in the audience, this was COVID time, so on the Zoom thing, I could see movement, that they would respond with movement to seeing that, more so than when I was demonstrating the actual sort of results when things looked normal and somewhat probably more boring. When things look crazy, you can see this like almost involuntary twitching of trying to like, how is that? And yeah, that really shaped my work a lot. So I guess the biggest sort of takeaway for me about the subjectivity challenge is this importance of shifting the views of your work, acknowledging that this is subjective. I don't have the right to go out and say, I have made a dance generation system, God forbid, which is creative. That's not up to me to say. I have to view it from multiple lenses and yeah.
So it's like creating an open proposal, basically.
Yes.
And then seeing how that reflects on people's own creative and practices. Great. Yeah, and I think that loops back into my provocative thoughts, quote unquote, on how to make these systems actually percolate real people's practices, so on. So thank you. Yeah, I'll stop here. Thank you.
Thank you so much.
I thank Associate Professor Sara Friedli Alawi for her contribution. At this point, we're going to have a short break. Let's reconvene in 10 minutes, 25 minutes to 3. Please be seated on time. Back. I then call on Professor Geraint A. Wiggins to close the ordinary opposition.
I hope you can hear me. Yes, good, thank you. So, as we say in my country, geachte kandidaat, thank you for inviting me to examine your thesis. This has been a very interesting experience for me, and so far today has been a very interesting experience for me. I'm going to cheekily borrow one of your own phrases. I look forward to being surprised in the next half hour or so. It's perhaps helpful, before I start asking you questions, to explain where my questions are coming from. My background is in both music and artificial intelligence, and I am particularly interested in the roots of creativity in cognition. And I think your work, even though it's not really intended in that direction, does actually shed some interesting light on cognitive aspects, specifically on cognitive aspects of all of this. So that's where I'm coming from. Of course, I'm not going to ask you to talk about things that are outside the scope of your thesis. I mean, don't worry about that. But I am going to ask you to speculate about things and perhaps to dig a little deeper into the consequences of the things you've done. Now, at some points in this, it may be entirely appropriate to say that is outside my remit, and it's okay to do that. Okay? Right. So then, the way I'm going to do this is by picking a few sentences from your thesis and, in some sense, throwing them back at you and asking you to dig deeper into them. So what I'm doing here is I'm asking you to go beyond what's in the thesis in a certain sense. I'm not asking you to clarify what's in the thesis. Yeah? Okay. So this is not nitpicking.
Okay.
Good. Okay. So then, my first question relates to something that is in the abstract of one of your papers here, the one called Towards Movement Generation with Audio Features. It says, sound and movement are closely coupled, particularly in dance. Yep, that's often true, okay? Certain audio features have been found to affect the way we move to music. That is also clearly true. And then you ask a question, and this is the interesting part. Is this relationship between sound and movement something which can be modeled using machine learning? The whole thesis is about this, right? This is the key question in the middle of the thesis, at least from my perspective as a technologist. What does that question mean? what does modeling mean in this context? Can you tell me what you think?
Yeah, I think by modeling, I'm thinking of being able to replicate, to mimic, and do so in a way that can be examined and prodded and hopefully reproduced.
Okay. All right, so there's a whole bunch of other sub-questions in there.
Okay, good.
Let's talk about the examination and prodding for a start.
Yeah.
If you do this using deep learning, how can you analyze what's going on? You showed us some very nice analyses,
Yeah.
actually, which goes way beyond what most people do in this kind of work. Maybe give us a little more on that?
Yeah, you're absolutely right. I mean, deep learning is not exactly the first choice of people who want to get a good overview of what's going on. It is very, as Sarah put it, it's opaque often, and you can't really retrace the steps in an easy way. There's obviously ways of using different methods to try and sort of have explainable AI kind of thing. I didn't go into that, obviously, in my own work. So for me, it's I guess reproducibility in the way that I can see it, that I can recognize it, and hopefully others also can.
Okay. So then, again, in a kind of a speculative mode,
Yeah.
what might a model be which would capture the subjectivity that lies within that mapping? So subjectivity, most people think of subjectivity as something being in the mind of the beholder. And most of your usage of the word
Yes.
here was that.
Yeah.
But there is a kind of a subjectivity which relates to all humans in the way we perceive the world, right? So we've discussed here, or you've discussed here, the idea of a mapping between X and Y,
Yeah.
sound movement and
Yeah.
generation and so on and so forth. Now, mathematically speaking, that mapping is simply a correlation, right? It's a function. Maybe the function generates values to drive your dance, or maybe it generates distributions from which you sample your dance.
Yeah.
That sums it up, okay. But that is another black box.
Yeah.
Do you think that's what humans are doing when they learn to dance, when they observe?
Could you?
Do
I'm
you
not
think-
sure I understood the.
So, the thing you've built behaves like
Yeah.
a human in the sense that it watches something, learns how
learns
to do
from
it,
it.
and then does it, right? But do you think that mapping that is being learned is a
Yeah.
good model of a human?
Definitely not the mapping that I have been doing.
Okay.
This directly sort of mapping. I mean, again, this goes back to these sort of somewhat awkward approximations that I've had to do. For example, how I represent the sound is that's a choice that I have made about what I think might be important features of the sound and that might affect how we move. It's obviously based on other people's research and other people's findings, and so I feel like I can sort of justify starting there, but none of this other research would go out and say, if you have pulse clarity and information about sub-band spectral flux between 500 and 6,000 hertz, then you will get the mapping between, you know, how you move differently to a dance track versus a ballad. Like, no one else is saying that, and in a way that is what I am sort of suggesting is could that be possible to break it down into these composite parts and find a a deep enough and wide enough and complex enough model that could actually be able to find these correlations in the form of those mappings that we can sort of observe with humans, but we're not really directly. I agree that there is no calculation going on in my mind whether, oh, the beat is of a sufficient clarity that I will now bob my knees up and down. There's no, I'm not making that calculation.
Not explicitly, maybe.
Specifically.
Yeah.
But there is there was I had a very interesting discussion with now a PhD student here, Diego Marin, who I worked with, who's a dancer and a dance anthropologist, about who owns the output of my model. Who made that dance? Is it me? I would say I am the lowest on the list. I did not have anything to do with that, in a way. Is it the dancers in my data set? Is it the algorithm? Like, who made it? Who owns it? And I was arguing that, no, I consider it to be the dancers in my data set. They taught this machine to generate some dance. And he very promptly sort of responded, oh, well, okay, so when I dance, is that the result of, is that the product belonging then to my dance teacher from when I was 6 and my dance teachers throughout my life? Does my dance belong to them? Which really put me in a position of like, I think it's a really good question, and it speaks to that, this thought of like how do humans learn, and what is this sort of special sauce that happens when we take what we've learned and then we use that to produce something that is personal and ours.
Okay, that's going to lead on to another question later.
Okay.
For the moment, I'm actually just as a footnote, Ars Electronica, which happened last week, had its whole theme, who owns the truth? And the answer that your colleague gave was strikingly absent, I have to say. But anyway, let's not get into that. So yes, my previous question you answered in terms of audio analysis almost. And that's an interesting one. What about in terms of dance analysis? Your system, with its different, with its Gaussian mixture, you were capable of interpreting that in some sense. You were able to give us some kind of interpretation there. Are you able to give us, do you think, any kind of indication of how you could go further with that? And specifically, what I mean is, I was kind of surprised that you've got these 4 dimensions, which I assume is produced by some kind of dimensionality reduction, or just within the network?
Actually, it's just it's super simplified. Obviously, the explanation I gave, each of those Gaussian distributions are like 22 times 22 joints. Each of the joints has its own distribution.
Okay.
Yeah.
Okay. Well, maybe that's going to be the answer to my question. So let me edit my question slightly. First of all, how did you choose the 4 that you have there? How did you generate those from whatever else was there? And in particular, if it were done in another way, do you think we would start to see maybe more than 4 useful dimensions?
Well, so the mixture density network sort of, the number of distributions is a hyperparameter. I set that parameter before training. So I tried out a couple between like 3 and 10. Obviously, since there are then 22 joints, each of those have 3 dimensions, and so it's 66 times number of mixture components for every time step. So lots of mixture components means I need to beg for more time on our servers to train the models. Like, it becomes so big. So I couldn't really try anything bigger than that here, which again goes sort of back to this notion of how limited we are in being able to answer a lot of these interesting questions of like what would be possible, just because there's obviously limits on data and how and time. I mean, if I had trained a model big enough, it probably would still be running today, right? And so there are things I can't try out, but what we found with the different numbers of components, mixture components, was, at least in my experience, and this is, I guess, more anecdotal than anything else, that there would be quite a clear drop-off for between sort of the 2 or 3 most likely distributions to sample from, they would have something that was you could see like this is a human, it's moving. Whether or not it's good dance is obviously up to interpretation, but then it would sort of fall off quite rapidly for the other distributions, and you would get something that either stood completely still or was like not really connected or didn't seem to have a human shape at all.
Okay.
So I don't know if it would help to have just a lot more.
So here's a related question. Did you do any kind of correlation analysis? So the nature of the model you have means that there's quite likely to be correlation between the parameters for particular joints, right? So particular movements would cause that. Did you do that kind of analysis?
No, not really. I think one of the things that I would have loved to do more of is basically the dance analysis, like approaching the generated output with that kind of a lens and trying to draw more of a correlation between what the model learns to do and does most of the time, what roots that has in the data set. So I'm afraid I didn't really do any of that analysis during the thesis work, but I think it has a lot of potential to have some really interesting responses in there or results in there. Of course, it would depend on the model you choose and everything, but just we did a small test where sort of I plotted some of the movement features of the dancers across the data set, and then I generated from my model 3 examples for each song, equivalent to what a dancer in the data set would have done, and sort of plotted against to see if it sort of fell into the close to the mean of the group or what it did. And it was quite erratic. The AI was very much an outlier compared to the other dancers, which I thought was very interesting, but we unfortunately didn't really spend much time on looking at that kind of stuff.
Okay, I mean, maybe surprising because the AI doesn't have the physical constraints that dancers have.
Yeah.
I said surprising, I should have said unsurprising.
Yeah.
Yeah, because there are lots of constraints there for the dancers that do not apply in the network. Yeah. Okay, so then to come back to the earlier, the point that you made about, you implied about how do humans do this from just learning? Right? This business about generation and creativity. And in another one, there's no point in my finding the reference, you talk about generative dance, by which you mean dance which is generated by AI, right? Yeah. To be absolutely clear, that's fine.
Yes.
But in the same sentence, you use the word create.
Yes.
In our field of computational creativity, sometimes we refer to that as the C word, because it's the word that nobody wants to say because it's so difficult.
Yeah.
So what is the difference between generation and creativity?
Yeah, I definitely did use the word create, meaning produce, and not the capital C, create. Several times in my thesis, I had to, just as like an aside, I had to really laugh when I got the topic for my trial lecture, because I've also discussed a lot with my colleagues, especially Ritmo colleagues, about this, like the C word, and with some of my fellow PhD students, we were sort of like, let's just not use the word creativity in our thesis. Let's just not touch it. Let's find other words to use, because we don't want to start that whole discussion. But, and then I have this trial lecture where I think I said creativity probably 200 times today. So now I'm in it, like now I have to talk about it. But in that specific sense, when I say that the generative model creates something, I did mean it with a small c, but I guess your question is more, what's the difference between producing and capital C creating?
I'm asking for your opinion.
Yeah.
How can we make movements from small c to big C, if you want to put it in those terms?
Yeah. Yeah, that's... think I have to think a little bit, because I think it's extremely difficult to know. How would I recognize that when I've gone from small c to big C? How many people would have to tell me that was really creative, what your model just did? Is it just one? Is it like the majority of people? Does it have to come from someone who has merit to say these things? And I don't really know. And I think that's part of this whole of me trying to find a phrase which ended up being the subjectivity challenge, to sort of try and encapsulate this big complex idea of evaluation. And
Okay, so let me challenge that, if
Yeah.
I may. That kind of presupposes that the difference between, shall we call it trivial creativity, everyday creativity, and big creativity, whatever
Yep.
that
Yep.
is in the evaluation.
yeah,
Is it necessary? Could it not be in the nature of what is going on?
personally, I don't think so.
Okay,
I don't think. I mean,
all right, I'm going to challenge you then.
yes,
Let me give you an
please
example.
do. I'm
Let
very
me give
curious.
you an example. So in the early 20th century, Arnold Schoenberg, who is a name that many people in the room probably know, became one of the most important modernist composers of art music in the 20th century, because he decided to make a change in the way music was produced. So he said to himself, I mean, this is now me quoting his letters, so this is a reasonably accurate description of what he thought. He decided that music over the previous 100 years had become more and more chromatic. That's to say, broadly speaking, using more and more of the potential 12 notes of the scale, as opposed to the 8 that were conventionally used before that. That's a simplification, but it'll do. Now, so he said to himself, well, why don't we go the whole hog and use all of them all the time in exactly the same statistical balance? Now, I would propose that a simulation of Schoenberg, or a simulation of Schoenberg's musicality, which had been trained only on music from the previous 100 years, or maybe 400 years, would be incapable of making that suggestion. Because what the models that we're talking about doing here are generating incredibly detailed statistical models, or stochastic models, if you will, of what exists.
Yes, yeah, of history.
So what do you think about that? Do you think it's possible that a model of this kind could make that kind of change?
I agree that obviously, yes, it is this problem of sort of expecting something new from a model of historical data is, I can see the argument for why that would be impossible. But at the same time, well, yeah, I see what you mean regarding this sort of, with Bowden's clarification of it as being like transformational creativity, if that would be possible. And I guess usually when I try and think about this and just speculate about these things, it is the kinds of things that we saw with the hide and seek example that I gave. There is some inbuilt sort of stochasticity that can produce things that were not present in the data set. And I think whether or not these things are sufficient to sort of be transformational does depend on the person viewing.
So whether it's transformational or not depends whether the change is big enough in some
Yes.
sense. Yeah. That's a reasonable position, I think, yeah?
Yeah.
So then, here's an interesting one which relates directly to what you just said. the maze example that you showed us
Yeah.
was a great way to finish. Actually, you covered 3 different learning methods in your talk, almost without us noticing, which was brilliant.
Good.
I thought. That one is the only one of the
Yeah.
3 which does random search, which is
Yes.
capable actually of coming up with new things that it
Yes.
hasn't seen before.
Yeah, true.
And is that not fundamentally important here?
I think it is a big part. I think again, as I was saying to Sarah as well, there's been a big weight on my shoulders in many ways with this work, the fact that I use supervised learning, because I feel like it just includes or introduces this like deep down in the basement like evil thing of like, haha, actually I'm still saying that there's a ground truth, and so what you believe about creativity sort of I'm breaking that. And I think that reinforcement learning, these approaches, and perhaps, especially things like intrinsic motivation and these kinds of reinforcement learning models have more of a potential to like, if I was in a dream world where I was researching what is creativity with a big C, and I was not afraid of it at all, and like everyone let me research that, then definitely reinforcement learning would be sort of the path that I think I would start going down. And I wouldn't touch supervised learning at all, and I would see what happens with that kind of a model. I think it has more potential for this transformational sort of creativity.
Okay, yes, I think I probably agree with you there. Okay, so then a related question, but coming back to the idea of a model which already exists. Something, again, coming from my own work in music, something that you sometimes hear people say, especially if they're listeners to music which is intended to be listened to as opposed to danced to, is something like, that surprises me every time I hear it. Now, that sounds like a contradiction, right? Because it implies they've heard it lots of times, so why should it surprise them?
Yeah.
And you talked about surprise in your thesis. Where does surprise, how is surprise going to influence the models? So surprise was very much to do with the output of the model in your work.
Yes.
But how could surprise influence the model itself in order to do something that is more perhaps interesting or challenging to a human?
Yeah, that's very interesting, because I think for example, when I was working on this second paper where we would feed the model sort of these unseen examples, like music features, and ask it to generate some dance, which I guess you could see as a sort of us trying to surprise the model with like, what about these features? And what happened was it kind of broke down a little bit. Like, it didn't handle it in a particularly interesting way, in my opinion at least. It was sort of more of an addition of noise. Now I've thought a lot afterwards about things that might be interesting to change about that study and take it maybe a bit further. We were using priming, for example, so we would constrain the model to what kind of movements it could predict in a way. And if we didn't, then maybe this addition of new sound features would cause more interesting output. But from my experiences solely in the thesis work, the model does not take kindly to surprise, as opposed to how I experienced this with the dancers, for example, who were very positive.
So does that not mean that your model was overfitting?
It absolutely might be, yeah. Especially in that early paper, that could have been the case. We obviously sort of implemented the best practices of early stopping and to try and sort of mitigate and make sure that we were not overfitting. But at least to me, that's kind of what the results somewhat looked like, that they were overfitting. I think way that we could have tested that would be by not using primed sampling and letting it generate based on its own previous predictions to see if that gave us a different output.
Okay.
So I'll do that this afternoon just to test. So I've been thinking
Could have
about
a
it
rest
a
this
lot these
afternoon.
days.
Yes. Okay. Just trying to decide if I want to follow that up any further. I've gone completely off my planned list here, but that's okay because it's really interesting. Can you see ways in which you could direct the behavior of the network more in respect of human performance? So, I mean, literally the dancers, you know, what would be expected of a dancer, which could then focus surprise in the content of the dance rather than in other parts of the mapping which are perhaps less relevant to that. Are you familiar with ways that might happen, or things that you could apply to your network, or new layers that you could build on top, or so on?
So, do you then mean directing the behavior of the model post-training in like an interaction setting?
Maybe, or maybe during training. I mean,
Yeah.
is there a way that you could make the model aware of how surprising its output was,
Yeah.
and then to act on that?
I feel like you just made light bulbs go off for lots of people at Ritmo now. They're like, yeah, pupillometry, like heart rates, we do all that stuff. There are physiological responses that we could, in theory, sort of map back into the model on the fly or during training in some way.
But your model doesn't have physiological responses.
No.
So how could
then
it look at
we would
its
have
own
to-
output?
Sorry?
How could it look at its own output, maybe?
That the model's own output could be evaluated by the model to determine how surprising it might be to humans.
Yeah. Do you think we could do that kind of thing?
I think I would have to say that would be difficult and maybe even not a particularly good idea. I guess
Okay.
just because it brings me back to this, like, surprising to who? When we were doing the work with the case study with the single dancer over time, working with Glitch, he obviously got to know some of this behavior that initially was to him very like, oh, what's happening? And then after he worked with this interface over several weeks, and so after a time, like the surprise dims, and it doesn't have that same cause that same response in him. That's why he ended up turning it on his students instead, to surprise them. So I think that I don't know how I would begin to try and quantify surprise. I guess there are some there are some studies, I guess, on this sort of like the curve, this almost like a bit of a sharp bell curve for novelty and what is it, like arousal or something?
The Wundt curve.
Yes, exactly. So it would be potentially interesting. We did sort of play around with this with a group of students who published on trying to use reinforcement learning on dance generation, and they used that as the reward function, like similarity to the things that it had already seen. And then if it hit this like sweet spot, it was given a high reward. So maybe, but that does, then I would have to admit that there is like one thing that quantifies surprise, and I do believe that it is so different between the individuals.
Right, so it's a complex function of many variables.
Yes.
Absolutely. Yeah. Okay. All right then, my last set of questions is to do with time and sequence, which you referred to very clearly in your talk and in your lecture this morning. When we perceive continuous movement, or continuous anything in the world, we have habits of breaking it up into sections. So when you perceive a dancer making a particular move, it's a very complicated set of sections, but we perceive boundaries, even where there are not technically boundaries, in some kind of measurement. Do you think that it is important that a dance system of this kind should have that kind of ability to understand the temporal structure in a sense which is perhaps a little more discrete than what is evidently a very continuous model at the moment? Do you think that's important?
Well, yes, it is part of a consideration that I made. I mean, for example, dividing space into discrete areas, or just dividing the dance sequences into sets of sort of discrete poses, and you could treat them almost like a language, where a sentence is maybe an 8-second movement sequence, and each pose would be a word, and you could just interpolate between the two. This also makes a much more sparse representation than the dense one that I've used. So, but I made a sort of an active choice to not do that, and keep things as, I guess, open, and because then you would have to put some restraints that I wanted to avoid. But yeah, I guess it would be possible and also interesting to see what would happen if we experimented more with sort of both the lengths of the sequences, or treating it as a sequence at all. But I guess from my experience, the way that we produce movement and perceive movement seems to be similar to how we produce and perceive music, where it is not like isolated events. It is a continuous story that's being told, and what you did 30 seconds ago has an effect on what you do now. They color each other, and so yeah, I would say that I think it's an important thing, to view it that way.
So maybe we could build something on top of a network like this to find that higher level structure, maybe, or something.
Yeah.
Which then brings us very nicely to my last question, which is about long-term dependency.
Yeah.
So that came up in your, was it the lecture this morning, or I can't remember which, but it's come up in your presentations.
Yeah.
Do you think that is important here? And if so, is it a problem?
I think that at the later stages of my work, I shifted from an LSTM to a transformer model and tried that out as well. And there is definitely an interesting shift that sort of happens, where there's also technical benefits, like the MDRNN, especially when it's smaller, more fewer layers, it would have this tendency to sort of freeze up after a while. Like the movements would get slower and slower, and then it would just stop moving. And the transformer model allows us to sort of circumvent that, and so this sort of window of attention, now I mean that like figuratively, and changing that definitely seems to have a big impact on the movements that are generated.
And do you think that produces better movements?
Yeah.
Movements, whatever that means, or?
Yeah, in my opinion, yes. It's more it's more coherent, and you get more of a feeling of a story, of something evolving and changing over time. Yeah.
So there again, it's like music, right?
It is, yeah. Yeah. At least I've chosen to think of it a lot in that way. I mean, I am not much of a dancer myself. I have more, if anything, of a music background, And so I think it was very natural for me to think of dance as more closely to my previous title, right? This like multi-dimensional time series data. So I do believe that that is important, but I would be interested in hearing if any dancers would challenge that and say that maybe there's some type of dance that I'm not aware of where things are much more like isolated little moments, but yeah.
Okay. I think we could talk about that last part, the isolated little moments, for some time, but I think we should not.
Yeah.
So that is the end of my questions.
Okay.
Thank you very much.
Thank you so much. Thank you.
I want to thank Professor Gerard A. Wiggins for his assistance. And now for you. Does anyone want to speak ex auditorio? Does not seem like it. Then the committee will withdraw to evaluate the disputation. Has the committee found the disputation satisfactory? Yes. On behalf of the Department of Informatics, I would like to congratulate the candidate. A report will be made to the Faculty of Mathematics and Natural Sciences, and I hereby declare that these proceedings are concluded. And before we end, there will be a reception downstairs in the Ritmo kitchen, so let's all meet again down there. Thank you.